I will talk today about the future of quantum computers. Right now, somewhere in the world, a quantum computer just solved a problem. A problem that would have taken the world's fastest supercomputer the lifetime of the universe to crack. This is not science fiction, but it is 2026. We have entered the era of quantum utility, where quantum devices, despite their noise, can do something useful that defies classical simulation. But what is next? Beyond the press releases and the qubit count arms race, what does the actual scientific and technological roadmap look like? To answer these two questions, we need to go beyond the hype. We will explore the three frontiers that will define the next decade of quantum computing: the Hardware Crucible, the Algorithmic Frontier, and the Integration Challenge. This is the future, built on physics, engineering, and computer science. First, the hardware. The media loves to talk about qubit numbers, a 1,000 qubit machine, but for scientists, that is a nearly meaningless metric. The real metrics are quantum volume, qubit fidelity, and coherence time. Think of it like building a city. Qubits, or quantum bits, are the population. But if your citizens, qubits, are error-prone, cannot talk to each other, connectivity, and die off quickly, decoherence, your city collapses. The future is not about raw population, but it is about citizen quality and infrastructure. We are in the NSQ era, noisy intermediate-scale quantum. The next decade will be about getting FTQC, fault-tolerant quantum computing. This requires logical qubits. One robust, error-corrected logical qubit might need 1,000 plus physical qubits of incredibly high fidelity. Our first, small fault-tolerant machine is the true milestone we are racing toward. The contenders are the superconducting qubits, Google, IBM, the Sprint athletes. Fast gates, scalable microfabrication, but need near absolute zero temperatures. The trapped ions, Quantinuum, IonQ, are the precision artists. Incredibly high fidelity and long coherence, but slower and harder to scale. Neutral atoms, QERA, atom computing, are the dark horses. Arrays of atoms and optical tweezers offer incredible reconfigurability and potential for novel simulation. The wildcard, topological qubits. Microsoft building qubits from exotic quasiparticles that are inherently protected from error. If they crack it, it changes everything. The verdict, the future is likely heterogeneous. Different qubit types for different tasks, linked via quantum networks. Hardware is nothing without software. So what will we compute? Forget breaking all encryption. That is a specific, distant application. The near and midterm future is these three pillars. 1. Quantum simulation, the original dream simulating quantum mechanics itself. This means designing new catalysts for carbon capture, discovering high-temperature superconductors, or engineering novel pharmaceuticals at the molecular level. This is not just faster, but it is impossible for classical computers at a fundamental level. 2. Quantum optimization, finding the best solution in a vast landscape of possibilities. Think hyper-efficient global logistics, revolutionary financial portfolio strategies, or optimizing complex manufacturing processes. NSQ-era algorithms like QoA are already being tested here. 3. Quantum machine learning, QML, is the most speculative and potentially explosive frontier. Quantum models could find patterns in data that are invisible to classical AI. Imagine training an AI on quantum data from a chemistry experiment, or accelerating the core linear algebra at the heart of all deep learning. The key insight: the killer app won't be one app. It will be a classical quantum hybrid workflow. A pharmaceutical company will use a quantum computer to simulate 100 promising molecular configurations, then pipe those results to a classical AI and lab robots for testing. This leads to the third, most under-discussed frontier: integration. A quantum computer will never be a standalone machine. It is an accelerator. Think of it as the GPU of the quantum world. The future stack looks like this. 1. Classical pre/post processing. Your laptop prepares the problem and interprets the noisy quantum result. 2. Quantum control layer. a symphony of microwave pulses, lasers, and cryogenic control systems, the real engineering marvel. 3. The QPU itself, sitting in a dilution refrigerator colder than deep space. 4. Quantum classical feedback loop, hybrid algorithms constantly shuttling data back and forth. Access will be almost exclusively cloud-based. You won't buy a quantum computer. You will buy time on a quantum resource, just like you rent GPU clusters from AWS or Google Cloud today. This democratizes access and creates a whole new software and service economy. So, let us map this to a realistic timeline. First, from now to 2028, the InduSQ utility era, we are here. Demonstrating clear quantum advantage on specific, esoteric problems. Focus on error mitigation, not correction. Development of algorithmic tools for chemistry, materials, and finance. The training wheels phase. Second, from 2029 to 2035, the scaling and correction era. First demonstrations of small-scale quantum error correction. Logical qubits become a reality. The race to scale from tens to hundreds of logical qubits begins. The first commercially valuable, proprietary algorithms emerge in R&D labs. Third, from 2035 to 2040 plus the inflection point. Machines with 100-plus robust logical qubits can run Shor's algorithm for breaking RSA, 2048 in principle, but more importantly, they can perform large-scale, commercially decisive simulations and optimizations. Quantum computing becomes a standard tool in the R&D arsenal of Fortune 500 companies. The future of quantum computing is not a binary switch from classical to quantum. It is the addition of a new, fundamental layer to our computational stack. We went from mechanical to vacuum tubes, to transistors, to integrated circuits. Each layer did not replace the last, but it unlocked entirely new problem domains. Quantum is that next layer. It will not run your web browser or play a video game. It will help us solve the problems we cannot solve today, problems rooted in the quantum nature of reality itself. The goal is not to make our current computers faster, but it is to give us a new kind of lens through which to see the universe. The next decade is about the hard, unglamorous work of engineering quality, writing clever algorithms, and building the bridges between our classical world and this quantum one. The race is not just for supremacy, but it is for a new tool to tackle humanity's grand challenges. If you want to dive deeper into the physics of a specific qubit type, let me know in the comments. Thank you for watching.